Hi, I'm Avinash Subramanian. I'm working on modeling, simulation, and control at Julia Hub, discussing accelerating MPC with machine learning, and particularly with emphasis on the JuliaSim suite of tools. So, first of all, presenting an overview of the MPC suite in JuliaSim. So, how MPC works, I think of it as having three separate pieces. So you would have like an optimization module over here. So what that does is it simulates the dynamic model forward in time and then calculates the optimal control actions that would give you closest to your reference or closest to any objective you desire. And then once you get these control actions from the optimizer, you would pass the first of these control actions into the system, which in this case is the actually deployed real-world system. And at the next time step, you would get a measurement from that real-world system, which in general you would not be able to measure all your states. So there would often be a third step, which is state estimation, which is some sort of Kalman filter or the nonlinear variance of this. So in the JuliaSim suite of tools, we are able to do a wide variety of this different configurations, so linear, nonlinear dynamics, linear or nonlinear observers, and also getting models from modeling toolkit, Julia FMUs. So in terms of speed and performance, and here the control inputs, like speed matters because the control inputs need to be available to the real-world system within a specific time frame. So we're able to solve like linear MPC problems with about 4,000 hertz, nonlinear MPC problems with about 1,000 hertz, and surrogатized at up to 1 million hertz. So the last is what I'd like to talk about. So in terms of a workflow, there are a few different pieces. So one would normally build a nonlinear model, say with modeling toolkit, and then if one wants to work on linearization, so linear MPC, there's this optional trim and linearization function, and then there is the open source low-level particle filters package that deals with state estimation, and then one would package all these different pieces up into an MPC problem in JuliaSim control, and if one requires further speed, that would involve MPC surrogates, which are trained with Flux and CUDA. So as a stylized example, so this would be a nonlinear research civil aircraft model, and why we chose this is because it has fast nonlinear dynamics, so like a sample time of like 0.02 seconds, and it's of intermediate complexity, so it's not really a toy problem. And the idea is you have 9 states, which are the forward velocity, sideways velocity, and vertical velocity, and then you have the rotational angles about these 9 states as other states, rotational angles and velocities. And you have 5 control inputs, which would be the rudder, aileron, tail, and the 2 kind of engine throttles. So again, the first step is usually symbolic modeling with modeling toolkit or JL, defining variables, equations as kind of expected. And just as I'll try to make this larger. Or yeah, so just as quite straightforward, and also define equations. So this commonly comes from domain knowledge, and in this case, it is this kind of large mechanistic model that one would use over here. Following this, so in this case, MTK automatically gives the LaTeXified version of these equations, as one can see over here. Following this, one can perform the structural simplification in modeling toolkit, and then we kind of compress this large 123 system of equations to basically 9 equations with 9 equations and yeah, basically, and 9 reduced states, although they are somewhat nasty equations. So the next step, again, this is optional for linearization, is to use the trim functionality. So this basically gives you an equilibrium point or a point close to what you desire, which may not be an equilibrium point. if that's what's desired. And following this, one may linearize about its equilibrium point to get a state space model in delta coordinates. So then moving on to the state estimation piece, there are these functions that allow you to define in low-level particle filters various kinds of linear, nonlinear state observers, so one passing dynamics and measurement functions from the real model, and then one would also pass in this case, Gaussian noise model, so the covariance matrices for the process and measurement noise. Then lastly, one would package everything into an MPC problem, and then there are various types that are offered. So it could be a linear MPC, quadratic MPC. It could also be like arbitrary functions, so economic MPC and robust MPC and so on, all of which are fully featured. So particular to this talk, the idea is to kind of get a sense of the philosophy of surrogatization with this MPC surrogates to JL package. So we have so far primarily looked at the standard MPC, and this here the control law is defined implicitly through the optimization. But the idea here is if this is the optimizer, it's basically one way of looking at it. If we want to just surrogatize the optimizer, is it's a static mapping from the state estimate and the reference to the control law. So one can get like an explicit so one way of doing surrogatization is to get an explicit control law. To train a neural network to get this explicit control law. So that's this sort of middle approach, which we think is sort of more suitable for this case. And alternatively, one may want to just surrogatize everything, which is both the optimizer and the state estimator. And there's some advantages and disadvantages of this. In that case, it will be a dynamic surrogate. So looking at the middle case as what I think would be most useful. So MPC surrogates provides basically a set of tools where one would pass in the MPC problem and get out a trained surrogate of the control law. So and then this can be, so they're good defaults, but these can be kind of configured. So since it would, like in the middle case, it would be a vanilla neural network. So would have a depth width, and you can set these parameters and training parameters, and then call this get surrogatize function and return a trained neural network surrogate. So if just to quickly show the procedure of the above steps, so we could have linear MPC, nonlinear MPC, and so on, and nonlinear MPC with disturbance, and so on. So and then one can get the surrogate model, surrogate of the MPC here, and then we can plot the results of the surrogate, the explicit surrogate law from MPC surrogates versus the implicit one through the optimizer. And we basically see, even for a fairly intermediate complexity example, we are able to get line-over-line performance here. And this is in a case where the disturbance has never been seen by the circuit before. So, and in terms of speed, it is in the order of, so this is in the order of 22,000 hertz, where the optimizer is in the order of 3,000 hertz. And then, so the target is to get between 10 and 100 times faster. So MPC surrogates overloads this common solve functionality. So one would pass in this MPC problem and the surrogate controller, and then this can be used to simulate with the explicit controller. All right, thank you.